Welcome to Module 1, and we're getting into Module 1.4. This is, or not Module 1.4, Objective 1.4. So we were just carrying on with the physics that I need to cover in Module 1. So we're going to be discussing the lens system. So the lens systems is really important in remote sensing because of two things. First of all of our sensors have lenses. Second of all of our atmosphere is a lens. So we are constantly working through this and trying to deal with lenses. But before we get too far into the lenses, we have to understand mirrors. And now with mirrors, the reason I talk about mirrors is because this explains a lot about what we see in our images. Because we are looking at a reflected signal, whether it be from the sun to the sensor or whether it be from the sensor to the sensor. And that energy needs to interact with the target in some way. So that's what the mirrors are for, and that's why I have this introduction. So with mirrors, we have an incident ray and we have a reflected ray. We also have something called a normal to the mirror. The normal is always 90 degrees to the mirror, and the incident ray in a pure mirror is always equal to the reflected ray, so that the angle is anyways. And if it's a perfect mirror, then the actual energy will be 100% the same as well. So what I have a little picture over here on the side is just showing how a mirror kind of works and what we're actually seeing. So we have the mirror, we have let's say the top of this object, which has a height from A to B, and then it's going to move towards the mirror. So once it hits the mirror, like straight on, the angle that it goes at, it continues straight through the mirror. So we know that with a flat mirror, at the same, well, all the way along, doesn't matter what distance we are from the mirror, the height is not going to change if we keep a direct 90 degrees to that mirror. If we change the distance, for example, of this dark blue arrow to about halfway, it's going to make this also look like it's halfway. So this is the reflection. And we consider that an image, where the real life stuff is considered an object. Now we're looking at angles. If this let's say if we put an eyeball here at the end of this arrow and it was looking down, then it would see the head of this arrow. Down here too, so let's say this arrow is looking to the bottom of this mirror. It's going to look down and it's going to see something that is in this spot here. So the mirror itself doesn't converge or diverge any rays or anything like that, merely just redirects. So it's important to know that. So when we're dealing with a smooth surface that's acting like a mirror, and this is called spectral reflection, and we'll get into that a little bit later. But the spectral reflection or the mirror reflection takes all of the energy that comes along the incident ray and reflects it directly away at the exact same angle that incident ray came in from the normal. To change things up, though, we need to talk about spherical mirrors because we have a round Earth. We also have round atmosphere. So spherical mirrors are important to understand. They have what we call a principal axis that comes through. It cuts at 90 degrees, or the center of the mirror, a curved mirror. And then we have F, which is known as a focal length. And then we have C, which is the center of reflection. Center of curvature, not reflection. And then we have the radius. So the radius is not always the same as the focal point, because the focal point here takes in a concave mirror. So there's a terminology for this. So a concave mirror, the energy comes along on the top, it's going to hit the mirror and it's going to reflect down, and it passes through the same point. No matter where it goes on the mirror, if it comes from up here and it hits the mirror up here, it's going to reflect down right through the focal point. The center of radius and the radius, these are terms that you would find in your equations when we get to the equations. So concave mirrors are known as converging mirrors because it focuses all the energy into one spot. If we have a convex mirror, we have the exact same components, except now the focal point and the center of radius and the radius, they're the center of curvature and the radius, are on the other side of the mirror. So we don't actually see them. But what it causes is the divergence of the light. So it actually makes everything appear bigger. So in terms of mirrors, okay, this switches up a little bit later. So convex mirror diverges the energy. Concave mirror will converge the energy. Then we get into the mirror equation and magnification. So this is just an equation that comes every time you talk about mirrors. You just have to show it because it is, and understand it because it is part of mirrors. So I have a distance object and an image distance, right? So remember that, where d, the full distance from the mirror to the object was, and then vice versa on the other side of the mirror. And then there's the focal length. So these are more for, this is for your spherical mirrors. We have our focal length, or we have the radius. Now, usually we're trying to solve for either di or do. So di is a measure for us that we actually physically can't measure on the ground, where do we can. Say, okay, I know that my satellite is, 9,000 kilometers from the surface of the Earth. So I can take that measurement from my distance of my object. I know what the focal length is of the satellite sensor because I designed it. And then I can figure out how big is that object going to be on my image. So this actually helps define for me my spatial resolution, because now I know how big my pixel is going to be when it comes into the sensor. If I want to see that object and I am at this distance, how big does my pixel need to be? Because it's got to go through all that. So that's where you'll see this being used. Another one that we have is the magnification. So this is just a simple ratio. So if the image size, so this is whether it be length or width, doesn't matter. The O represents the object size. So again, it just has to be the same as what you're measuring with the image size. And then di over do. Now, what does it mean when I have I, which is smaller than O? So if we do a quick ratio there, it means that, so if I is smaller than O, it's going to be less than 1. So if it's less than 1, the distance of I has to be less than the distance of O as well. So we know that if a value is less than 1, it means that it actually got smaller, right? Because the I is smaller. Or if we look at this one here, the distance of the object actually appears to be closer. If we reverse that and say, okay, what happens if O is smaller? Now it's greater than 1. And that means that the do, it has to be actually closer. So the distance has to be shorter than the object here. So then if it's greater than 1, then the image means the image size is actually bigger, which means it's now magnified. And the other one, it was not. It was made smaller. So that's the relationship there. So that leads into lenses. And so why are lenses important? Well, first of all, they cause refraction. They cause the light to bend. And they bend, and we can control the light bending based on how we design the lens. We know that this happens in the atmosphere, so if we have to do any kind of atmospheric modeling to accommodate for radiometric issues, which we'll get to later, but with the satellite itself, if it's acquiring information, what has happened as that light has moved through the atmosphere? And then I mentioned this before, but we have converging and diverging. So converging brings light rays together, diverging spreads them apart. Now here we have a convex lens ray diagram. So the lens ray diagrams are really important. Hint, hint. Principal axis goes through the center of the lens all the time. And principal axis seems to go through the center of everything. Every time you talk about a diagram, if you have a principal axis, it goes through the center of it. Then we have an optical center. So in this case, for example, it's the exact center of um, the two different types of lenses, because we have two different types of curves. And so it's right in the middle, kind of the center of mass, if you can consider it that. Then we have a line that goes straight down that kind of cuts the lens in half, and that is known as the optical axis in the vertical direction. And then we have our focal length, which goes from the optical axis over to the focal point. It's also known as principal focus in lens ray diagrams. So you can either refer to it as focal point or you can refer to it as a principal focus. They're both the same. Then we go along there, and that our light rays, in this case, they come across and they all converge. So this is known as a converging lens. And they are the convex lens. So please don't confuse them with spherical mirrors. They're the opposite. So a convex lens, here's an example with an object. So I have my object standing there. If I have my light ray that goes all the way across here, it is going to basically hit my optical axis. It doesn't perfectly work that way, but it is generally how we model it. And then it comes down and goes through the focal point down to where we're going to create my real image. So object and real image. So this is known as a real image on the other side. It's just upside down. And then then we look at the A. So if it passes through the optical center, it doesn't go any other direction, which is similar to as if you were using a mirror. If you were going like straight to that center point of the mirror, well, no, the center point of the mirror just puts it to 90 degrees. So as we go through the optical center for a lens ray diagram, it passes through and does not change its direction. If we go from the top of the object down to the bottom where it passes through the focal point on the object side, it will come down and it will bend so that it actually comes to the top of the real image. So why is it called a real image even though it's upside down? Well, it's just because you can actually see it. So our eyes, our lenses are like this. They're built like this. They create a real image on the back of our eye, which is upside down, and it's our brain that turns it right side up. And then we have concave diagrams, lens ray diagrams, and this one shows that everything diverges. So you can see the light rays on the other side are diverging. The focal point is only on the one side, right? So it's only on the object side. And the optical center, if you have a light ray that goes through it, it's just going to keep going straight. Otherwise, it bends away. But a false projection, so like as if the light was to go backwards, we can draw a line to the focal point from all of the rays that are being diverged. So here in a lens ray diagram, we have our object, same idea, except this time now I have all my points going in different directions on the other side of the lens. And none of them actually go through the focal point on the other side of the lens. Instead, it is a projected angle of like C going through that focal point that will that would go through that focal point. But the C going straight across, the C here, which is on the other side of the lens, it projects back and creates this virtual image. So this virtual image is a smaller option, and it needs to be captured in a different way. So it's not the same as a real image because a real image can be easily captured by a camera. These ones cannot because it has to have like almost it needs to have a film before the lens, right? Which doesn't seem to make any sense because it's really hard to manage that. So capturing something this way is very difficult, and you can see how it is much smaller. That virtual image is much smaller in this case because just the nature of how they drew this. So real image is on the other side of the lens. A virtual image is on the front side of the lens with the object. So then we get into Lensmaker equations. Again, if we were to make this lots of fun, I could put in all kinds of equations for you to practice. So here is the Lensmaker equation, and we're looking at the focal length. So we have 1 over f, which is the focal length, and you can see that the focal length is the same on either side, and whether it's a concave or convex lens. Mu, which is the refractive index of the actual lens, because that depends on the composition of the lens as well. Then we have R1 and R2, and these two are the different radius or radii of curvature for each side of the lens. So you don't have to have the exact same radius of curvature for both lenses. You can change it up a little bit, and that's okay. So if you're looking for a magnifying glass, you're looking at a double convex magnifying glass. That's a double convex lens is what you're going to use for that. And that makes things bigger. But we haven't really described those yet. So we're going to get into module 1, or the objective 1.5, and that is comparing lens designs. This one's really short, so I'm just going to do this one really quick. And then in a new video, I am going to be covering the Objective 1.6. So here in the lens designs, here are the 6 major lens designs. So these have sometimes different names, so I'm going to name them for you. But here we have a biconvex. So the two bumpy, it looks like it's out, everything's outside. Or what am I looking for? It's like fat in the middle, narrow at top. There we go. We'll go with that. So it's fat in the middle, narrow at top. The plano-convex is still kind of fat in the middle, but has a flat side to it. And then convex concave, or also known as convexo-concave, you have it's still fat in the middle, but less so. So it's being kind of managed a little bit with this, with a little bit of a curve here. So you will see biconvex, also known as double convex. So you'll see that is another name. And these ones are known as my converging lenses. So these three are converging lenses. And if you're going to do the equations, they are considered positive lenses. So you use positive sign on it. Then on these last 3, we have a meniscus lens, which has a fatter top and a narrower middle. You can't see that here, but that's what it does. It is also known as a concavo-convex or concave-convex. So it has like 3 names, but that's what that one is. Then we have plano-concave, so we have a flat side, and it's fatter at the top and thinner in the middle. And then we have biconcave, which is fat at the top and thin in the middle, and it's a lot more drastic. And these last 3 are known as negative lenses, or also known as diverging lenses, and that's what they do. So we'll be getting into module 1.6 in the next video, and I will talk to you then, I guess.